Hello and welcome back. Further maths, in fact. Leibniz rule for differentiation. This is not a difficult topic. It's a little bit of number crunching. It's kind of like resembles the binomial. And I could be wrong on this one. It's the first time I actually see it at A level. It's because it's just tedious. It's not really anything complicated. And well, you just do it at university. You come across it a couple of times, but it's not of maths use most of the time. Okay. What does the question says? This question I'm going to put in one of my papers very soon. So I wrote it only yesterday. If y is x to the 4 e to the 3x, show that the kth derivative of this function, if I differentiate k times, the answer is e to the 3x times 3 to the k minus 4 times some function f of x and k to be found. So the question now is how we do a question like that. So I'm going to go in a little bit of detail. I'll try not to rush this particular one so we all follow what's going on. First of all, I'm going to write up here. I hope I can fit it because I need a lot of space for this. What the Leibniz rule for differentiation says. So d by dx, if I differentiate a product of functions, u and v's, where u is one function of x and v is another one, then the answer to this particular one is d u by dx. I'm going to be putting the derivatives in a minute. dv by dx. So that's the nth derivative here. And that's the 0th derivative. And 0th derivative is, of course, if you want, the kind of like the function itself. So a lot of the time when you see it in books, they just write v really. So that's 0 there and 0 there. Plus, then it goes like a binomial. N du by dx, dv by dx. And now we have n minus 1, n minus 1. And then we have, of course, 1 and 1. N binomial n minus 1 over 2 factorial d n minus 2 of u by dx, n minus 2 derivatives. And now this is a second derivative. And this is the dx squared plus, I can't even squeeze it in there, but you get the picture. N minus 1, n minus 2, 3 factorials, and then I'm going to have d third derivative of u with respect to x times the third derivative of u with respect to x plus dot 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 there, and it will terminate on the other end. Okay. So this is now what Leibniz rule says. So if we look at in now y, we have a product of two functions. It hardly matters what you call u and what you call v, but the way I've written it, I'm going to call u my exponential and v I'm going to call my x to the 4. And the reason I'm going to do that is because if you look at the differentiations of x to the 4 as I've written them here, that's an x to the 4, that's going to be a 4x cubed, 12x squared, 24x, and then it's going to be a 24. So after one more term, this will produce zeros. There's no need to write anything else. So let's go and start writing this. So it doesn't really matter whether you call the kth derivative or the nth derivative. So this is now the kth derivative, just to be consistent with how the question has been written, is x to the 4 e to the 3x. So the next thing is to understand, this is our u. How do I differentiate e to the 3x k times? This is a standard result, which you ought to know. So d by dx, for example, of, let's write it in k, of e to the ax, where a is some kind of constant. Every time you differentiate, an a comes to the front. So if you do it k times, you're going to get a to the k, e to the ax. It's kind of obvious, I'd like to think. So for something like that, if I differentiate, because that's my u now, I'm looking at that. If I differentiate that k times, I'm going to get 3. That's my a, basically. 3 to the k, e to the 3x, times this, which I rubbed it off, but that's actually just your v. So it's going to be times x to the 4. So that's the first term. Plus, let's not forget the k, because I didn't call it, I wrote it there in n, but the question for some bizarre reason has it in k's. So that's a k. Now I differentiate my u k minus 1 times. So now it's going to be times 3k minus 1 e to the 3x. So that's differentiating the u times differentiating now the v once. So it's going to be times 4x cubed. So that's this term. Plus, I'm going into that. I'm going to write the 2 factorial as a half. K minus 1. Very annoying, this k minus 1 now instead of n's. Differentiating now the exponential k minus 2 times. So it's going to give us 3 to the k minus 2 e to the 3x. And now we're differentiating the v twice. That's differentiated once. So that's going to be plus 12, no plus, I'm writing stupid things again, times 12x squared. Let's wrap that off because we're going to need a lot of space for this. And we're going now plus, we're going to 1, this will be factorial there, very stupid of me again, loads of mistakes, as you probably know with me. K minus 1, k minus 2, differentiating the exponential k minus 3 times is going to be times 3 to the k minus 3 e to the 3x, and now the third derivative, so that's the second of the v, so it's going to be times 24x, and I don't think I can actually fit the next one in there. So let's write on the next line. The next line, there would have been, of course, 4 factorial, which is 1 over 24, k minus 1, k minus 2, k minus 3. And you can see the pattern there. It's going to be times 3 to the k minus 4, e to the 3x. And now we have times 1 more derivative of that. So that's the third derivative there. So fourth derivative times 24 plus, I could say dot, but in fact, there's nothing else. And the reason there's nothing else is because when I come to do the next one, which is going to be the fifth derivative of v with respect to x, because of how I chose to do my functions, it's going to be x to the 4, 4x cubed, 12x squared. You can see all of these things there, 24x, then 24. But of course, now it's going to go to 0. So all the other terms, it doesn't matter what is at the front, will vanish. So now we need to do a bit of a tidy up in here with all of this. So what can we factorize in there? It's giving us a clue. Factorize e to the 3x, which of course is in every term. And the 3 to the k minus 4, that should be k minus 4 here. Another mistake. Look at the pattern, k minus 1, k minus 2, k minus 3, k minus 4. So let's do that. So we have e to the 3x times 3 to the k minus 4. Big square bracket. Okay, what do we have now in this particular quantity? The exponential has gone out. From this, I have, let me just write it, is 3 to the 4. Because these two, when they times out, they give me the 3 to the k. Hopefully you can see it. X to the 4. So that's this term here. Plus, gone. We have a k from there. And from this one, we're going to have now times 3 cubed. If you multiply this out, it's going to be k to the minus 1. Just check it. That is correct. And of course, after that, we have a 4x cubed. And we continue in the same fashion. A half k minus 1. These things will be there. This will be gone out. Times a 3 squared. Again, check it. 3 squared and 3 to the k minus 4 is going to give us 3 to the k minus 2 by adding the powers. The exponential, of course, is out. And of course, we got a 12x squared. From there, let's not forget it. And then we got plus. Very long, these questions. So you have to be careful. It's very easy to miss terms, and it's kind of like, as I said, a lot of number crunching. We can see the pattern: 3 to the 4, 3 cubed, 3 squared, times the 3 to the 1. Again, it does work. It gives you the k to the minus 3. The exponential gone out, and then we got the 24x, and we got, of course, some bits from there. 1 over 24. Very long chain of rubbish. K minus 2, k minus 3, up to here. This all gone out, this all gone out, and we've got times 24. So this is our answer, which I guess we can leave it like that, because technically it's of the form that times that, and all of this is a function of k's and x's, but I think we can do a little bit of a tidy up. So I'm just gonna write it up here. So let's make some space, because I think this will look a lot neater. Calculators are allowed, but it's not difficult. We don't really need a calculator for this. So what do we get? That was the k minus 4. So this is equal to e to the 3x times 3 to the k minus 4. And if we see what we got, what that f of x and k, 3 to the 4 is 81. X to the 4. 3 cubed 27 times 4, 108. K x cubed. Then we're having in there 12, 6, 9 times 6 is 54. K minus 1, x squared. Now we have this one. That's 1/6 of 24. Actually, we're going to do 3 times the 6, which is a half of 24, which in fact is a 12. Plus 12, we're on this term here. And then we go k minus 1, k minus 2. And then we got, of course, just x. And it's a shame we cannot fit again on that line, the very last term. The 24s will cancel. So the last bit only has k's, k minus 1, k minus 2, and a k minus 3. 1 over 24, and 24 has just cancelled out. So this is in fact our f of k. Was that a question that is difficult? No, it's just the same thing regurgitated over and over again. You just need to know some differential coefficients for the exponential function, for sines and causes, for shines and coshes. These are the kind of usual kind of questions they'll ask you. They're all the same. I'm not anticipating anything complicated to be asked for this particular topic. And as I said in the beginning, this is probably in further maths. I thought I'll do a question just to keep everybody happy as to how you deal with questions like that. I hope you find it useful. I'll be signing out. I'll see you real soon. Bye.